Hello, everybody, and welcome to another session in the Head Acoustics Educational Webinar Series. My name is Jacob Sondergaard, and I will be your host today. Today's topic is all about double talk testing. And as usual, I like to start us off with a quick look at the agenda. What we would like to do is introduce the topic of double talk to you and then talk about why it matters. It's always important to have some motivation behind all the slides that we're doing. So we'll make sure to emphasize that and mention that. From there, we'll move on to discussing some of the basic and fundamental tests that you can do to measure whether your device is double talk capable, or what we might call duplex capable. And then we'll talk about some of the more advanced double talk metrics that evaluate different things like attenuation and echo at once to give you a much better picture of how your device performs in the real world. After that, we're going to wrap this guy up and leave you with a few parting messages and wish you a wonderful day. So if you've been with us in the past sessions, you know that we've covered a lot of the basic tests in telecommunications, and we have even dipped our toes into some of the advanced tests, primarily echo. Today's topic, as I mentioned, is all about double talk as well as switching characteristics. Basically, it all falls under the umbrella of being able to duplex and handle signals in both the downlink direction and the uplink direction. Now, it maybe goes without saying, but double talk performance isn't necessarily something that impacts or matters for speech quality. Rather, this is all about conversational quality and the impact your device might have on conversational flow. So, with any communication device, a key part of what it has to do is to act as a communication bridge between two people. And if the product is unable or incapable of switching quickly, without attenuation, and without introducing echo, then we might have some issues for the users of your product. So you think about all the processing that is rolled into your product or any communication product today, and it ends up being actually quite a few different blocks consuming quite a lot of processing power, or MIPS, an actual amps and power and watts type of power. And especially for those of you that work in the mobile device field, so not just mobile phones, but also wireless accessories, things like Bluetooth headsets, for instance, that is taking on a lot more of the processing and running on a relatively short and low power battery. Double talk is something that requires extra attention just because of the power limitations you may have and even the processing limitations. But as we look at the green blocks in front of us today and we go through the test, we'll highlight some of the different ways that we can really drill down into the ability to test for duplexing and test for double talk performance. So before we dive all the way in, we like to start with an example. The example we have today uses two people counting all the way to 26. So if you guys were confused about how to count to 26 in English, we will get it into our heads today. But the reason why we do this is the best way for us to learn is really to listen and go through sort of a visceral experience, and listening to sound samples is a good way of doing it. Now, unfortunately, the audio playback through our GoToWebinar applet is limited to a single channel. So when I play this, all you will hear is one channel. Now, for the double talk example, where you have a male and a female counting, you won't get too much information out of it other than one side. When we actually listen to the uplink direction signals that include the near-end speech and the potential echo, it'll make total sense. But let me just play for you the single side of our counting example to get you guys into the framework of this sample we'll be using a lot throughout this webinar.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26.
All right, fantastic. We counted to 26, and of course what you didn't hear was the female voice. I believe you just hear the male voice counting, which is fine. Now, as you are mostly familiar with in telecommunications, we like to designate the near-end talker with a green color and the far-end talker with a red color. So you heard two different people counting. These signals will be applied to different ends of a telecommunications terminal or device. When we do that, we've taken two different devices that exhibit slightly different issues, but they're very common issues. The first one is a product that exhibits a few instances of echo. They'll be highlighted here in red, so when we play it back, listen for these sections in particular. And the bottom device, a little bit different, slightly different score as well, but this is a product that where echo necessarily isn't an issue. Rather, the issue here is clipping or attenuation of the near-end speech. Now remember, a lot of the double talk testing, we're in some parts stressing the onboard echo canceller. And what the echo canceller in part has to do, it has to evaluate the downlink signal and compare that downlink signal with what is going up from the near end. So typically the head and torso will be talking. Now, as the near end talker, what we would like to hear, as the far end talker, what we would like to hear is the hats talking to us. We want to hear every single utterance, every single number from 1 to 26. We want to hear without hearing our own voice bounce back up to us. So let me play the first file for you that exhibits some echo. And what you'll hear is the male voice is going to be the head and torso. So we want to hear the male counting. What we do not want to hear is the female voice. So we are the female talker in this case. We do not want to hear our own female voice bounce back to us, but pay attention to the first couple seconds and then some of the last seconds. The echo is audible and clear.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26.
So hopefully you heard and you detected that female voice being bounced back up. It's not that desirable to hear your own voice when you're on a call with somebody. And so when we analyze this using the P340 table, you can see that this would be classified as a type 2A product. Generally a good product, but still within the category that we call partial duplexing. Now let's listen to the other product that scores a 2C on the P340 classification table, which is also called partial duplexing. But now we'll listen to the issue of clipping. So now you should not detect the female voice. Rather, what you will hear is the near-end talker, the hats, using the male voice. However, that male voice is now going to be attenuated heavily or clipped in some cases, which makes some of those numbers not as audible.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26.
All right, so that was definitely different from our other device up here. And before we get into some more detail, I guess it sort of presents a little bit of a philosophical conundrum for us in if you could only tune for one parameter in your device, would you rather tune your device to have pretty decent near-end reproduction, although with some echo? Or would you rather tune your device so that there's zero echo, however, the near-end speech will be slightly or severely attenuated? Now, of course, I know that we can do better than that, because it is possible to tune a device so that you eliminate echo and you still get good near-end reproduction. However, in some cases, there are situations, let's say for emergency calling. So if we take the example from the automotive community of eCall, so if you're familiar with it, there's been a lot of evolution in the emergency call or eCall market in the automotive sector, where if you're in a crash, your vehicle, your onboard vehicle, has a separate black box device with a modem, a speaker, and a microphone built into it that is able to survive a crash separate from your audio system, that can make a 911 call and patch in a first responder. In that type of case, you might make some design decisions to say, I'm not really too concerned with echo as long as I can hear everything that's going on in the vehicle. What we don't want in that situation is clipping. The first responder cannot afford to lose vital information from the driver or passenger in a crashed vehicle, even if it means, hey, the dispatcher will get some of his or her own voice bounced back to them in the form of echo. So there maybe is a clear design choice where you compromise one deliberately in order to get absolutely bulletproof intelligibility and audibility by avoiding clipping. Now, for a general consumer product, your design decisions hopefully goes towards maximizing the performance in both categories. Zero echo, zero clipping, a perfect type 1 full duplexing device. That should be our benchmark, and that should be our goal. Now, we just had to listen to 2 examples, and subjectively, hopefully it was easy for you to detect the different elements that we want to avoid, and it was easy for us to evaluate. Yeah, they weren't great. The top one, okay, a little bit of echo. Bottom one, yeah, not bad, but a little bit of attenuation. However, if we had to do that and evaluate it subjectively during tuning and optimization and validation, that would result in a very time-consuming and expensive design process. But subjective testing does work, which is why the first method for evaluating double talk testing was subjective. However, the standards got together and said, we need something that's a little bit more objective. We need some form of metric and standardized procedure that we can run through a test system and allow us to evaluate the double talk performance. And the first one is a little bit of an amalgamation of different standards, but the one shown on screen here. And you can see that this was really just the very first baby step in getting some official testing and metrics on paper. Now, the first thing you'll notice is these look an awful lot like CSS bursts. That's because these are CSS bursts. Again, the red color signifies the downlink signal or the far end talker, and the green signifies the near end talker or the uplink direction. The CSS burst, of course, comes to us from ITU-T P501. Now, once again, I'd like to play this full signal for you. You're only going to get the one direction. It'll be very short. That's one of the benefits of CSS bursts, but I think you'll get a sense of what the CSS bursts sound like if for some reason you have forgotten. So I believe you hear the near end, so you heard 4 bursts followed by a single talk tone. Now, the second step in this double talk, the first double talk method, was to present these overlapping CSS bursts. So the black color on this chart signifies where we have overlap between far end and near end, and therefore where we have double talk. The second step is let's analyze that double talk according to the methods described in I2TP 501, where we essentially do level versus time analysis. And then the third part is once we have determined the attenuation that occurs in these black parts in the double talk, we can take that attenuation and plot it into the category table defined in I2TP 340. So on the previous slide with our counting example, I gave you some examples from a product that registered or scored a 2A and another product that scored a 2C, where all we're looking at is the attenuation. So very quickly, something that we consider a type 1, a full duplex capable product, is not allowed to exhibit more than 3 dB of attenuation during this double talk sections. Likewise, partial duplexing actually encompasses not only the 6 dB threshold, but also the 12 dB threshold. It's all considered partial, although, as you can imagine, there's a big difference between a product that attenuates, let's say, 3.1 dB versus something that attenuates 11.9 dB. And then finally, if for some reason you end up scoring greater than 12 dB of attenuation, you get a 3, which is a no duplex capable product. Not very good. Now, a point about delay, because not only does delay matter for echo cancellation, the other thing that delay does for us is if it is long enough, it could end up offsetting speech and introduce what we call unintended double talk. Now, the communication channel we're on today is a one-way direction. We've muted all you guys, and it's only my audio. But if I were to call you directly, and I was using my Bluetooth headset connected to my mobile phone, and I was in a poor cell tower area trying to call you, and you were likewise on your mobile phone and a Bluetooth accessory, the amount of delay that could be introduced by each processing block introduced by the network could lead to, whenever I talk and whenever I ask you a question, the time it takes for my question to actually reach your ears, I'm already starting to think about, hey, did you understand what I was saying? Did you even hear me? I should better rephrase my question or simply ask it again. In the meantime, you've heard my question and you're already responding exactly at the same time while I am asking you the question again, and we end up talking over each other, and it ends up breaking the conversational flow, and it ends up being a very frustrating situation. Remember that as human beings, we are inherently designed for what we call the orthotelephonic scenario. This is the high bar that we would like to achieve in telephony and communications. So remember, orthotelephonic scenario is when you and I sit 3 meters apart, 10 feet apart, in a room with no echo, no reverb, no background noise. And the only impairment is a limit to our vocal cords, our sense of hearing, and the slight acoustic delay from my mouth to your ear and vice versa. But that is what we ultimately want to get to. We want to get to as low a delay as possible with the same full, rich sound in terms of voice quality, with the same conversational flow and conversational quality that allows us to do things like double talk or talking over each other and still being able to process and understand all of that. And of course, ideally, something that is also a binaural or a stereo signal. We have 2 ears, and that's, I think, ultimately where we want to go with communication products. So the unintended double talk, of course, is also an issue that we have to account to when it comes to delays. And as I mentioned, with modern products, with wireless hands-free devices, with networks that sometimes are overloaded and packed to capacity, what we end up experiencing is a lot of delay introduced in each block and introduced by the network going in the uplink direction as well as in the downlink direction. And so when we talk about the orthotelephonic scenario, what human beings are used to, we talk about few milliseconds worth of delay. And in our previous example, we talked about maybe 300 milliseconds of offset that causes or gets close to introducing unintended double talk. And when we look at a typical hands-free situation today for a narrowband call and the amount of processing, the amount of delay, and we talk about typical values in the 200, maybe even 300 millisecond range, you can see how little we need to add to our signal chain in order to bump up our delays and make two-way conversation nearly unbearable, or at least frustrating, to the point where you almost revert to a military style push-to-talk level of communication, which, if you're trying to have friendly banter and a nice conversation with a spouse or a friend or a colleague, is not that conducive. Likewise, if you're trying to have a serious business discussion, it just doesn't work particularly well if you have to slow things down that way. So let's look at some of the metrics. And the first one that we want to look at is the issue of speech activation. The whole point here is we need to figure out, does your device even respond to double talk? Now, if you have push-to-talk devices, well, there's no real issue of double talk because a push-to-talk mechanism simply overrides the channels. It's not designed for double talk. But the fundamental issue here is a voice activity detector or an echo canceller could be either very slow to activate and converge, or simply the echo canceller is designed as a voice activity detector, in the sense that when there is no near-end speech, the uplink microphone is simply switched off. So we used to joke around that the world's cheapest echo canceller was a voice activity detector. Very few people go this route today, but the point was, in the good old days, you could fool something like a TCLW, if you remember those echo measurements, the echo loss measurement. You could fool a TCLW measurement by employing a voice activity detector as your echo canceller. But as soon as you got into situations with double talk, now how quickly does that voice activity detector wake up and allow the near-end speech without, of course, allowing echo to come back? You would see issues with clipping, loss of sounds, loss of syllables, loss of words, or even worse than that, loss of entire sentences. But that's what we want to look at with the speech activation. This is the very fundamental first step in figuring out, can your product even handle the idea of double talk? So not all standards include this particular test, but if we look in ITT P340, this is where we get the root of the speech activation. So the measurement process is to apply the CSS double talk signal, so uplink and downlink at the same time. And then remember, we only had 50 milliseconds of overlap, which, by the way, if you remember that stimulus signal we looked at, the double talk was only 50 milliseconds, the overlap between uplink and downlink. And you might think, is that really accurate? Does that tell us a lot about how the device performs? Because 50 milliseconds, you could argue, is almost too fast for the human ear to even respond. And likewise, another issue with this is we're using CSS burst, right? It's a little contrived. That's one of the knocks on CSS burst. It's fast, it's a great fast test stimulus, but is it a little too contrived? It sounds a lot like noise, remember? Not necessarily speech. In any case, that's the stimulus that was used for the good old double talk analysis method. So we apply that CSS-based double talk signal And then we look at the level versus time between our source signal, so what we know we're sending to the hat's mouth, and what the device actually sends up when there is double talk. So now we're looking at, does the echo canceller or the voice activity detector or AGC, do all of these processes somehow impact and influence the signal that is sent up when we know exactly what we sent to the device? Now, the key thing here is the method relies on you to do the analysis. So in my case, I went and looked at, so if we're looking at the time domain up here, you see the sources in blue. This is what we know we sent to the hat's mouth, and the green hidden behind it is what was sent from the device. And if we do the level versus time subtraction of the two, you can see that after a very short amount of time, this device converges, tracks very well what's going on with the source signal, and so the activation is very, very short. It's a good response for that particular device. Now on the bottom, we can see same thing. Source signal is in blue, and behind it, we have the green signal, which is the signal that the device sent up towards the far end. It's hard to see, but if we do the level versus time subtraction, you can see there's really no good tracking here. Everything's kind of all over the place. And somewhere around 81 milliseconds, according to me, because I am the analyst in this situation, I feel like things start to stabilize and we get some form of tracking. But you might look at this and say, well, maybe it's more like 70 milliseconds, or maybe it's 90. And that really depends on where you set the line, where you determine that things start to track pretty well. Now, the sister measurement to the activation is then to look at, once the device is activated and has activated, can it then do so without incurring too much attenuation? So same thing, we apply our CSS burst, but now we're concerned with what is the attenuation from the beginning of the utterance until things converge and we have a fully tracked response. Now, of course, what we're trying to evaluate is, if this attenuation is very, very high, it means that you have a great amount of loss and a great amount of clipping in the uplink direction signal. That's not what we want. And of course, the root of this could be voice activity detectors, echo cancellers, AGC, and in some cases for mobile devices or wireless accessories, it could be a power management issue. So the method is exactly the same as before. Apply the CSS double talk, but now we're looking at the y-axis. Instead of the x-axis and the time domain, now we're just looking at the difference between before the device converges and after. And in this case, me, the analyst, I have interpreted this top graph to show that we have about 13 dB of attenuation. So what that means is, if we use our ITU-T P340 classification table, is we have a class 3 device, basically a device that is incapable of duplexing. Now on the bottom, I feel like this attenuation is probably only on the order of 6 dB. So if I'm kind, I'll say a 2A, but maybe it's more like a 2B. In any case, it's much better than above. Now, the funny thing is, of course, this is all subjectively done, but this is maybe a little quicker than having to listen to a lot of audio files or speech files, but it still ultimately boils down to you as an analyst to interpret these files. And years ago, CTIA, the group CTIA, did a study asking audio experts, so in the field, audio experts in the field of telecommunications and audio processing and DSP, to evaluate many examples of double talk, where they looked at activation time as well as attenuation level. And not surprisingly, the study by CTA resulted in just radically different scores because each analyst saw slightly different things when it came to when things were stabilized, when things were converged, and what the actual anchor point was for your measurements. So even though it maybe improved things and sped things up in development, it still isn't and wasn't a particularly good method because there was way too much subjective, I don't want to say bias, but interpretation involved in the scoring process. So that's where the automated double talk method showed up. The big benefit here is, as you may have figured out, is that the evaluation process becomes automated because the actual test method is fairly the same. But because we now automate it, make it objective, it's a lot less subjective. So we use the same level versus time analysis, but going through some steps, some statistical based smoothing and analysis, we end up with some graphs that are a lot easier to interpret and can be interpreted automatically. Another cool thing with the ADT method is that you can now use this CSS burst for historical reasons or for time reasons, or you can use real speech for your test stimulus. And of course, everything that we preach here is as much as possible, let's move to real speech. This is what we want to do ultimately. Now let's take a look at the ADT method. So the first thing is we want to establish a baseline performance by just sending the single talk. So all we listen to is the hats talking. That is the ideal performance that the device can do when there's no downlink signal. We only get the hats talking to the device. Then we do the double talk test. So then we introduce, for instance, this overlapping CSS burst. So now we get the downlink interfering with the hats talking, but we measure what the device sends up during double talk. Then we do the subtraction of the level versus time from the single talk minus the level versus time from the double talk, thereby normalizing AGC and spectral content. We go through some of these mathematical processes in order to weed out some of the extremes. So this is part of the method and part of the standard where we exclude some of the odd outliers. And then we can calculate the attenuation range that occurs during double talk within sort of the normal range. And then depending on if you are using a CSS burst or real speech as your source file, you would either be looking for the maximum range of attenuation during double talk, or you would be looking for the median range. So there's a slight difference, and it is important, and it does matter. So if you compare the two, you can see that the CSS source method obviously uses the CSS speech. We have a much shorter time constant in our level versus time analysis, and we look for the maximum attenuation level. On the real speech side, obviously we use real speech, still grabbed from P501, but our level versus time constant is a lot longer, and we look for the median value, or the algorithm does. Also, for real speech, as you may be familiar with, the double talk section now includes both a bargain, so that would be a single word bargain. So if I'm having a conversation with you and you want to present your opinion, you might say, hey, you, no, yes, something very short, or call out my name, in order to literally barge in to my stream of consciousness. Or you might get so frustrated that you simply just start talking to me. That's what we would call full sentence or complete double talk. The real speech or the real speech stimulus will include both that bargain, the very short single word interruption during double talk, as well as the full sentence double talk. So you can evaluate for both. Now let's look at a real example here that always makes things easier. The first thing is we have a handset on the left-hand side that we evaluated using the CSS method and the real speech method. And you can see very quickly looking at the numbers, right, average or peak attenuation rather for CSS was 3.8 dB, which technically gives us a type 2A product. Using real speech for the bargain, the single word interruption, you can see we end up with a type 1. There's only 1.4 dB of average or median attenuation. And for the full sentence, we had a 3.3 dB median attenuation, which is a type 2A. So sort of overall, the methods do agree, although the numbers do differ. So let me play you what a good product sounds like, or basically this product sounds like in handset mode. I know you guys are already looking on the right-hand side and looking at the numbers, but let me present to you what it is supposed to sound like. This is a pretty good product. And then afterwards we'll take a look at the handheld hands-free situation.
5, 5, 5,
5, 5, 5, 5.
5,
The shaky barn fell with a loud crash.
pluck the bright rose without leaves.
A pencil with black lead writes best.
The glow deepened in the eyes of the sweet girl.
All right, so what you should have heard is somebody saying 5, basically a very short word, and we want to hear every single syllable in that word 5. This occurs at varying degrees of double talk, but we should be able to detect all of them, and that should be pretty clear from this recording. Likewise, here you have the ITU P501 sentences, the Harvard sentences phonetically balanced. You should be able to very clearly hear all of them, maybe with some slight clipping occurring during some of the words in the sentence. Now let's put that very nice performing device in handset mode to handheld hands-free. So it's a mobile phone put out in front of you in speakerphone mode, and you can see scoring it using the CSS method gives you 13.8 dB of peak loss, basically a type 3, not good, not duplexing capable. Now, using real speech, same classification, but you can see that the median attenuation is all of a sudden very, very different. And of course, the beauty of using real speech is we can play this back and listen to it and subjectively validate, is this making sense? Does this actually tell us the correct things? So let me play you these two, and I think you can agree the attenuation that occurs here is horrendous. So basically we have whole words completely missing from this playback.
5, 5,
5, 5, 5. The shaky barn fell with a
pluck the bright rose without
pencil with black lead.
in the eyes.
So clearly not good. Way too much information. And I guess the question is, would you be happy with this, right? If you were on the other end of that call and this is all that came back to you on the far end, you would be pretty upset with their device and their echo canceller. And so you'd immediately ask that person who made your device and tell them to improve their echo canceller, because this is not good. Now, shifting gears a little bit, because this next method uses our good old mosquito buzz test sequence. So that's the one that sounds like just a swarm of mosquitoes coming at you in two-channel form. But the reason why this method is so interesting is because it highlights to us, or it highlights in the frequency domain where there might be issues with the echo canceller. So if you haven't heard it before. I will play it for you. Of course, we can only get one channel and we can only get the uplink direction. So the idea is that in red, your device will be receiving a swarm of mosquitoes, and then the hats, sort of halfway through, will start to chime in with his own mosquito-like tone. But as you can see from our spectrum below, the frequency content from the hat's mouth in green versus the frequency content from the far end is slightly shifted. That allows us to do some pretty cool analysis in the frequency domain to check for not only attenuation, but also echo. So let me very quickly play this for you, just so you get a sense of what that sounds like. And we can go look at the analysis. So that would just be the tone, the mosquito tone, mosquito buzz noise coming out of the hat's mouth. Now, of course, your first response is, wow, that does not sound like real speech at all. And you're right. So, use this with a little bit of caution, because some modern devices might say, I'm going to reject this. This does not sound like speech. But for the time being, we've had a lot of success using this stimulus file to test devices and evaluate attenuation and echo in the frequency domain. So the idea here is that we can now, because of the offset frequencies, we can now look at the attenuation and the echo. This example, we'll look at the attenuation. So in the green, we have what the device sent during single talk. So the test method is constructed to where we first play out just the hat's mouth, and then we can play out the full double talk sequence afterwards with both the downlink and the uplink signal. And we look at the sending direction for single talk, and then we look at, well, what did the device actually send up when we had double talk? And you can see here for the very low frequencies, 250 hertz, we have very high attenuation between the ideal scenario, which is single talk, and the scenario where we did have double talk. Now the device is not sending nearly as much information to us at low frequencies, and so at this particular single frequency, we can classify the device as a type 3. Basically, this would not work for duplexing or double talk. Now, as we step through each of the frequency bands, you can see that our attenuation drops, meaning our categories go up. So now we're in a type 2B, bordering on a 2A. And now already at 750 hertz, give or take, we have about 3 dB of attenuation and basically what we would call a type 1. So as we step through the frequencies, we can evaluate this in the frequency domain to see if there's anything specifically with our echo canceller or other processes on board that we need to rectify, which may not show up in something like TCLW measurements or eQuest measurements for echo, things like that. So we step through and eventually we end up at the very higher frequencies where it appears for our device here that we're somewhere in the noise floor. Now, let's look at the echo that occurs during double talk. And again, in the frequency domain, we use exactly the same stimulus files before, but now we take advantage of the offset frequencies. So in this case, the blue curve here is what is sent to the device under test during double talk. And the red is what the device sent in the uplink direction during double talk. So what we would want to avoid is the device echoing any of the blue signals back up, i.e. shown by the red curve mirroring the blue curve. So very low frequencies, we don't see any echo at all. But as we start to step through the frequencies, you can see that the spectral shapes, they start to align, meaning that when our device is receiving the signal during double talk and it is sending this back up, we know that this wasn't generated locally. This is an issue with the echo canceller at 1300 hertz that is going to be a real issue. Likewise at 1700 and so on. There's clearly an echo signal being bounced back up to the far end, which is not generated locally. You can see it finally starts to subside at about 3100 hertz. Let me play this file for you, because what you'll hear here is the traces of echo in the midband, and then you'll hear the near end talk, and then you'll hear the traces of echo afterwards. So let's just have a listen to that. So once again, subjectively, easy to tell, we had echo issues, but using this method, we're able to drill in and see exactly where in the frequency domain our echo canceller was exhibiting issues. Now let's spend a little bit of time talking about the speech-based double talk metric that comes to us from 3GPP, because this is a very, very cool metric. I don't want you to get overwhelmed by the colors and charts here, because we'll step through it step by step. But the very quick overview is that this is a method that allows us to evaluate both gain, so echo, and attenuation, clipping, with one test method and one analysis method. The process is very similar to the automated double talk method, where we still use a level versus time subtraction, and then we simply take that level versus time subtraction and we slot it in on this color-coded chart and use our lookup table to figure out what category are we in and for how long are we in each category. So let's first of all go through the process of measuring this. First thing is, let's establish our baseline. Now, this is a method that only works with real speech. No more of the CSS stuff. This is real speech. The first thing we want to do is we want to play out a couple of samples of speech in both the uplink direction and in the downlink direction, so that we know the device is completely activated, completely converged, fully engaged, and then the downlink signal switches off at about 30 seconds in, and all we hear is the hats talking. The hats will be saying 5, 5, 5, and then a couple of Harvard sentences at the end. That establishes our baseline performance. Now, the next thing we do is we take the same first 30 seconds of some uplink speech and downlink speech to make sure everything's activated and converged. But now, it's going to be a little hard for you to detect in the top right-hand corner, but our hats going 5, 5, 5 and Harvard sentences is still going on, except we'll have that downlink stream of consciousness presented to the device to see how well does that device now transmit the hat speech without, of course, looping back or echoing back the downlink speech. So now we have the level versus time for our baseline and single talk. We have our level versus time analysis for our double talk performance. We do a subtraction to normalize things out. And then we can start to look at each double talk section. So we split it up into the bargain section, which is sort of these 15 or so seconds here, and the last 15 or so seconds will be the full long sentences of double talk. And then we'll slot these onto the categorization table that I presented on the slide before. So with the A1, A2, B, C, D, E, F, G, and so on, to figure out what type of performance can we classify that device with for double talk. So let's go through an example that usually helps. So the first thing we have here is an example of a bargain. In red and in black here is a downlink stream of consciousness to the device, and then we have a single utterance, 5, being spoken out by the hats. So I'm not going to play that because you know what the word 5 sounds like. Now, if we take just this utterance here and present it to the device, unfortunately, our device ends up only transmitting what's shown in green, or rather the overlap is going to be in black. So the blue curve in that middle graph is going to be the full word 5. This is what we send to the hat's mouth. Unfortunately, for whatever reason, voice activity detector, echo canceller, power management issues, AGC, for whatever reason, it takes such a long time for the device to activate that the only thing we get out of it is this last little bit out of 5. It's basically just V. And I'll play that for you so you can hear the difference between what we want and what we get.
5.
So clearly, listening to it, immediately we're alerted to something is wrong. Looking at the time graph, immediately we're alerted to the fact that there's a lot of content missing here. Now, if we do the level versus time subtraction, we can also see that there's a big difference presented like this. Now let's use our chart or our table to start to classify this double talk segment. Now, fortunately for us, there's a little bit of time here where we are in what we call the A1 category. That's the plus minus 4 dB graph. That's good, but man, there's not enough of it. Now, A2, okay, it's still reasonable. It's still full duplexing, or at least partial, because we are incurring some attenuation. And then, unfortunately, you can see we're spending a lot of time in category C, and we're spending even more time in category D. Category D means it's any loss that exceeds 15 dB and exceeds 150 milliseconds in duration. Now, we also have to slot in the top here, which is basically the echo parameters. You can see that we don't have any, well, maybe just a hair worth of echo at the end here. But in general, this product does not have an issue with echo, but it has a severe problem with clipping or attenuation. Now, if we then tally things up, or let the algorithm tally things up, what we end up with is, you can see we spend 17% of our time in A1. That's good, but we really want that to be 60, 70, 80%, ideally 100, but 17% is not enough. Good thing is there's not a lot of loss there. So as you go down through the chart, you can see that class D, the biggest offender here, we're spending 58% of our time exhibiting 27 dB of loss, ultimately resulting in a huge amount of clipping. And that's basically what we see here. It's what we heard from this audio file. The only thing we really detect is this last little bit, the V in 5. That's the only thing that really comes through. Everything else, you see very quickly, bang, we just lose everything, the front syllable. And that's what this method is telling us. And it's surprising. I know this comes to us from 3GPP and the mobile phone community, but it doesn't matter what device you're doing, whether it's a hands-free device, whether it's a wireless accessory, whether it's a headset or a handset or some unknown shape. This method is very strong and works very well for classifying the double talk performance of those devices and shows such good correlation with subjective evaluation. We just listened to this. This is just one example, but every time I have done this and I have listened to this, I look at the classification table and I think, yeah, that is actually very, very close and very good, and I would probably score it very similar. But I don't have to because the method does it for me. So if you're not using this already, I would encourage you to look into this method for evaluating the double talk performance, because it really captures everything from activation time to the amount of attenuation to potential echo as well. So with that, we're coming up on the hour. I'd like to wrap things up by leaving you with just these few take-home messages. The first thing is, of course, double talk is really an issue, a factor for conversational quality or conversational flow. Every millisecond of delay that is added to the communication channel could make double talk impossible or frustrating at best. So you want to mind your processing time that you allocate to duplexing and echo cancellation. We presented several different metrics from the very basic fundamental analyst-based methods to some of the more automated, including the speech-based double talk method from 3GPP. And they each have their pros and cons, but they're actually getting to be very, very good. And then finally, for some of the later metrics, what we end up with is using real speech recordings, which we can use as a fallback for subjective listening, so that if there is any doubt, you can listen to the results and do your own evaluation. So with that, I appreciate your attendance. Thank you very much for dialing in and hanging out with us today. We hope you have a wonderful day.